Greetings. Today I'm going to do my presentation backwards. I'm going to tell you what I bring to the table. An idea to make an inexpensive thermal camera more usable, and defer the discussion on why people are interested in thermal cameras towards the end of this video. The reason I want to do this is because if you are interested in watching this video, it is likely that you already know the use cases for thermal cameras. Doing it this way allows you to get to the interesting what and how first. If you already know the use cases, you can skip the why part at the end. Now, let's get started. Many people ask why thermal cameras are so expensive. There are a number of reasons. 1. Thermal cameras are not mass-produced like visible light cameras, meaning that they have not achieved the economy of scale. 2. Infrared detectors require use of exotic material like gallium arsenide, which add to the cost. 3. Thermal camera lenses cannot use glass. Glass is not crystal clear in the range of wavelength used by infrared sensors. They require use of rare elements like germanium. This further adds to the cost of thermal sensors. And the most expensive thermal cameras use cool thermal sensors because the heat generated by the sensor and thermal camera will affect the accuracy of the temperature readings. Not too long ago, when you talk about inexpensive thermal cameras costing tens of dollars instead of thousands of dollars, these thermal cameras were mostly using the Panasonic AMG 8833 thermal sensors, which has an 8 by 8 pixel resolution. Compare that to the resolution you are familiar with, like on your notebook or desktop, like usually better than 1080p, right? And then came the Malasys ML9640, which has a resolution of 32 by 24. You would have thought that, wow, it's a much needed improvement. But is that enough? How does it compare to higher end thermal cameras on the market? Now, let us compare the images produced by products on the market. First of all, have a look at the FLIR E5-XT, which has a resolution of 160 by 120 pixels and costs around US $14.99. You can see quite a bit of details in here. Now let's have a look at cheaper ones based on the MLX9640 sensor. The one we're looking at is called the M5 Stick T-Lite thermal camera. It costs $79 US. You can see in here, you cannot see too much details. Here is my challenge to you. I'm going to show you some thermal images and see if you can tell what you are looking at. In here, what is this? Not much detail in the image, thermal image. What if you can see this? You can clearly see that this is me waving at you. Or you can see my face in the second photo as well, second image as well. Right. I'm going to tell you how I achieved this later on. What about the next challenge? What is this? I bet you cannot tell what it is. What about now? You can see clearly that this is the keyboard of my notebook. You can see the hotspots in here. what about this? You can see clearly that is a keyboard on my notebook. Third challenge. This is the most difficult one. What is this? Last chance. Let me show you. This is actually a soldering iron that you're looking at, but looking at the thermal image, you can never tell. And here is alternate augment image. How did I do it? How did I augment the low resolution thermal images with details so that you can tell what you're looking at? It has been proven in the previous challenges that you could not tell from the low resolution thermal images alone. The trick here is I'm actually using two cameras. The first camera is the M5 stick T-Lite thermal camera, which I mentioned earlier. The second is just a normal visible light camera. I'm using the M5 camera PSFrame ESP32 based camera. As I said, I use two cameras. I reprogrammed a normal camera into a RTSP server to stream real-time videos to an endpoint. RTSP stands for Real-Time Streaming Protocol. The M5 Stack T-Lite thermal camera comes with lots of capability. One in particular I like is that it provides a REST API to get the thermal image. What I've done is I've written a OpenCV application which scales, smooths, and overlaps the images reading from both cameras. So basically what it does is it captures the stream from the RTSP server and it executes a get to get the thermal image, and then overlap the two, scale, smooths, and overlap the two images, provide you with the augment image that you saw in the earlier challenges. This program has been containerized. That means you can run it on Podman, Docker, MicroShift, OpenShift, or other Kubernetes variants. Most people use smoke and mirrors, but I'd like to use a small shipping box and some rubber bands to hack together a prototype, although I wish I had a 3D printer. Now let me show you the OpenCV application user interface. On the left hand side, you can see the image. Either it's the thermal image, the normal image, or the overlapped image. What you see is controlled by the panel on the right hand side. On the top of the right panel, you'll see a temperature summary display, which displays the average, center, minimum, and maximum temperature of the thermal image. Just below it, you'll see the options. The first option is image processing algorithms, adaptive arithmetic, mean thresholding, and none. These options apply to the normal camera only. Initially, I implemented several different algorithms, but the adaptive arithmetic mean thresholding looks best. Let me show you each option and how it looks like. This is using no image processing algorithms. If I choose this, you can see this. This is especially useful when you are looking at something in a low light situation, because when you're choosing none, sometimes it's very difficult to see the image of the normal camera. Next, you see the thermal camera image color maps. So it controls the color. You see the color gradients. Like if I go back to thermal camera only, and I choose the Inferno, so you see you have a totally different color map, which is showed here. Let's go back to Jet. I think Jet looks more retro. And at the bottom, you have the display, which controls whether you are seeing just the thermal camera or the normal camera or both. When you select thermal camera, you see an extra panel in here. You can see here is some arrows. So you can see in here, because I'm using a hacked to create a prototype, they're all fastened together. All the cameras are fastened together using rubber bands. So there may be some alignment issues. For example, if you look at it here, you can see that the thermal image is a bit to the right. So what I can actually do is either I adjust the cameras, or I use these controls to do that. So for example, I want to move the thermal camera to the left. I can do this. Move it up a little bit. In the low light situation, as I said, in the low light situation, you cannot see my face. So when you're using the LUN option here, but if you use the adaptive arithmetic, you can see the outline of my body. As I said in the beginning of this video, I'm leaving the discussion of thermal camera use cases till the end. And here is only a very small sample of the use cases. If you're interested, you can Google the topic and you'll find a lot more use cases. I'm not going to go through every one of them, so I would just give you some time to go over these use cases. In this video, I showed you how to add details to the images from a low-resolution thermal camera by using an additional normal camera. You have seen the result and how that was achieved. I hope you find this video interesting. One last thing, all documentations, including the architecture, video link, and source code, can be found in my GitHub repository. Thanks for watching. Until the next time, stay safe.